Hello everyone, this is Rakesh Kumar from EC department. As you all know, we have discussed till now the architecture and pin diagram of 8051. Now we will discuss its memory organization. First of all, we have 128 byte of RAM for 8051. Basically, the RAM has an address range from 00 to 7FH. This 128 bytes is further divided into three different groups. First group is of 32 byte, that is reserved for its register bank and its stack, and it ranges from 00 to 1F. Next group is of 16 byte, that is reserved for bit addressable, and it ranges from 20H to 2FH. And its last third group, that is of 80 bytes, has location from 30H to 7FH, and it is used for read and write storage. This is called a scratch pad. At the right side, you can see the 128 byte structure, that is starting from the register bank 0, register bank 1, register bank 2, register bank 3. All these are the banks of register. For different types of registers we will discuss further it. Next is bit addressable area and general purpose area. All these comes under 128 byte of RAM, that is from 00H to 7FH. Now next is RAM address range. As we know, RAM is of size 128 byte. 128 byte means 2 raised to power 7 bytes. That means the last 7 bits can be changed. If we start from 0 towards 7, these are total of 8 bits, and its initial address that makes the 4 times 0 and 4 times 0, that is the 00H, and the final address is 0 1 1 1 1 1 1, that is the 7FH. As we have 2 raised to power 7, so we can change its 7 bits. The 7th 0 will remain the same, that is the 7F range. This procedure is called the memory mapping. How we can map the RAM address range? This is the memory mapping from which we can address the RAM in its different sections, that is from 00H to 7FH. This slide also shows the RAM address that we already have discussed. As you can see here, the register bank 0 ranges from 00H to 7H, and register bank 1, that is the stack we will use in 8051, and it ranges from 08 to 0F. Next is register bank 2, that ranges from 10H to 17H. 18H to 1FH range is reserved for register bank 3. From the bottom 00H to 1FH, all these sections are reserved for register bank. As we have 4 registers bank in 8051, that is the bank 0, bank 1, bank 2, and bank 3. Next is the range 20H to 2FH, that is the bit addressable RAM. Next is the scratch pad, that is the read and write area, that ranges from 30H to 7FH. Next is the 8051 register bank structure. As we already discussed, we have 4 register banks in 8051, First one is the bank 0. It further contains 8 registers that ranges from R0 to R7. Next is the bank 1 that also contains the 8 registers R0 to R7. Next is the bank 2, bank 3. All these register banks includes 8 different types of registers in it. This slide shows the register bank area, that is the register bank 0, 1, 2 and 3 with its different ranges starting from 00 from the left side, starting from the 00 to 07 is reserved for bank 0. Register bank 1 ranges from 08 to 0FH. Register bank 2 ranges from 10H to 17F, 7H. Register bank 3 ranges from 18H to 1FH. This is the structure of a register bank of 8051 that we will use for storage purpose. Actually, register banks are used for temporary storage purpose. Next is the 4 KB ROM of 8051. A ROM, as all we know, is available for program storage, and it is the permanent memory. Also, it is the volatile memory. The data doesn't lost after power failure. That's why ROM is called the volatile memory. This ROM is also called program memory or code memory. The size of ROM is 4 KB. That means 2 raised to power 2, and KB can be rewritten as 2 raised to power 10 because 1 KB is equal to 2 raised to power 10 byte, and it makes the total of 4 KB ROM in 2 raised to power 12 bytes. That means the last 12 bits can be changed in this. And this 4 KB ROM addresses ranges from 4 times 0H to 0FFFH, as you can see in this slide. That is address range of program counter is 4 times 0H to 0FFFH, where we can save our program. This also shows the address range of internal and external ROM. Now next slides comes with the special function register that we use in 8051. We have total of 21 special function register. All these shows the 21 range of special function registers starting from F0 to 80. In this, B shows the B register, C shows the accumulator, PSW is the program status word. All the ports 1, 2, 3 and port 0, stack pointer, data pointer with lower byte bit and higher byte bit, P-cone and T-cone registers. We will discuss it further. First slide come with the register A. A is also called the accumulator. Accumulator is a type of register that we use while performing any kind of operation, any kind of programming operation. One of the data should be in the accumulator and other may be in memory or a register. And after that, the result of the operation will be stored in this register A, that is the accumulator. Its size is 8-bit. From bit 0 to bit 7, you can see. Next is the register B. Actually, register B is used with the accumulator only, and it is used in multiplication and division program operation. It is also of 8-bit, that is the bit 0 to bit 7. Next is the data pointer, that is the DPTR. It consists of two separate registers, DPH, that is the data pointer high, and DPL, that is the data pointer low. For this reason, it may be treated as 16-bit register. Actually, DPH is the 8-bit and DPL is also the 8-bit, and both of these combiningly makes its size of 16-bit. As we have two independent 8-bit registers, that is the DPH and DPL. All these are the data pointer registers, and we further have divided it into 8-bit slot. Their 16 bits are primarily used for external memory addressing. Besides, the DPTR register is usually used for storing data and intermediate results. You can see in this picture that DPTR, that is of 16-bit size, has been further divided into 8 bits. 8-bit is reserved for DPL and 8 bits are reserved for DPH. Next is the stack pointer register. It is also of 8-bit from bit 0 to bit 7, as you can see in the image. A value stored in the stack pointer points to the first free stack address and permits stack availability. Stack increments the value of the stack pointer by 1. Likewise, stack pops decrement its value by the same number 1. Upon any reset and power on, the value 7 is stored in the stack pointer, which means that the space of the RAM reserved for the stack starts at this location. As you can see in the previous slide where we have discussed the register bank. From bank 1, stack pointer is started. Next is the IP, that is the interrupt priority, used to indicate the relative priority of the each interrupt. Which interrupt has to be firstly served, that depends upon its priority. An interrupt may be of 0 or high priority. Next is the interrupt enable. It is used to enable or disable the specific interrupts. If we want to enable any type of interrupt, then we have to make the pin IE should be enabled, and if we will have to disable all the interrupts, then we will make IE disable. For making it enable, we have to write it with the high signal, and for disabling, we have to send it to the 0 instruction. Bits from 0 to 6 of the register EI are used to enable and disable the particular interrupts, whereas MSB, that is the most significant bit, is used to enable or disable all the interrupts. MSB is the master bit, that is the most left bit used in the 8-bit format. Next slides come with the program status word, that is the PSW. It is the very important register of 8051 that tells us the status of the operation. Whether the operation has been performed or not, we can check from this register. It is of 8-bit. All these sections have different functions. P stands for the priority. OB is the overflow flag. RS 0 and 1 are the register select. AC is the auxiliary carry and C is the carry. C means that is the carry flag. If a carry is generated, then it will give the status about that. Next is the AC, that is the auxiliary carry. If any auxiliary carry will be generated in the operation, then it will show us that status. F0 and dash, that are the user flags 0 and 1. We will not use both of these register because these are user defined. OV is the overflow flag. If the result of any 8-bit instruction will be overflow from the 8-bit result, then this will show that status. P is the parity bit, and it shows whether the parity bit has been generated in the result or not after any operation, maybe after addition, subtraction, division or multiplication. Now RS0 and RS1 are the register bank select. This is the table for RS0 and RS1. If both the RS0 and RS1 bits are 00, then bank 0 will be selected. If we have to select bank 3, that is the last in the chart, then we will have to give 1 to both the registers RS0 and RS1 with 1 1. If bank 1 will be selected, then RS1 must be 0 and RS0 must be 1. This is the structure that we can select any register bank by using both of these bits in the program status word of 8051. It is used to indicate arithmetic condition of accumulator. The flag register in 8051 is called the program status word because in the PSW we have all the flags, that is the carry flag, auxiliary flag, overflow flag, and the parity flag. That's why the flag register in 8051 is called the program status word. It is of 8-bit in size and 2 bits are unused as these are the user definable flags, and we use only 6 bits in 8051 while performing its operations. D0 is the parity bit, as we already have discussed it. For even result of accumulator, parity flag should be 1, and for odd result of accumulator, parity flag should be 0. It is mainly used during data transmit and receive via serial communication. D1 for further version of microcontroller still not have come. D2 is the overflow flag. OV is set to 1 when result of a signed number operation is too large, causing the high order bit to overflow into the signed bit. That is, OV is only used to detect errors in signed arithmetic operations. D3 and D4 are for register bank selection, as we already have discussed. By default, initially bank 0 will be selected. To make RS0, we have to write a command, that is the set bit PSW 0.3, and for making it 0, we have to write a command, that is the CLR PSW 0.4. Both of these set and clear are used to set the register and clear the register. D5, that is the F0, it is also available for user for general purpose. D6 is the auxiliary carry flag. When carry is generated from D3 to D4, as you can see in this addition of binary to 8-bit binary addition, if a carry is generated from D3 to D4, then this auxiliary carry flag will be 1. It is used in BCD arithmetic. Next is the D7, that is the carry flag. When a carry is generated by performing addition of two 8-bit numbers, if a carry is generated, then this flag will be 0, will be set to 1. Next is the 8051 stack. Actually, stack is the section of RAM used by the CPUs to store the information temporarily. This information could be data or an address, and it works on the principle of last in first out, that is the LIFO principle. The register used to access the stack is called the stack pointer. Actually, stack pointer access the stack, that is the stack pointer stacks register, and it is called as the stack pointer. Stack pointer in 8051 is the only 8-bit wide, which means that it can take value from 00 to FFH because its size is 8-bit, so it ranges from 00 to FFH. When 8051 is powered up, the stack pointer register contains the value 07 as we have discussed, that is the starting of register bank 1. RAM location 08 is the first location begin used for the stack by 8051. The storing of a CPU register in the stack is called a push command. Stack pointer is pointing to the last used location of the stack. As we push data onto the stack pointer is incremented by 1. This is different from many microprocessors. Loading the content of the stack back into the CPU register is called the pop. With every pop, the top byte of the stack is copied to the register specified by the instruction, and the stack pointer is decremented once. Thank you.